Advanced Engineering Physics. Unit 1. Crystallography and Materials Characterization. Crystallographic planes and directions. In crystallography, understanding the arrangement of atoms is important, but equally important is understanding the orientation of planes and directions within a crystal. These planes and directions help us describe crystal growth, cleavage, slip systems, X-ray diffraction, and many other physical properties of materials. Let us first study crystallographic planes and the concept of Miller indices. A plane in three-dimensional space is uniquely determined by three non-collinear points. In a crystal, there are infinitely many planes passing through atoms in different orientations. To specify the orientation of a plane conveniently, crystallographers use a special notation known as Miller indices. Miller indices are represented by three integers enclosed within parentheses, such as open parentheses, HKL close parentheses. These indices provide a simple mathematical way to identify the orientation of a plane relative to the crystallographic axes. The Miller indices of a plane are defined as the smallest set of integers obtained from the reciprocals of the intercepts made by the plane on the crystallographic axes. An important point to remember is that the symbol HKL does not represent a single plane. Instead, it represents an infinite set of parallel and equally spaced planes throughout the crystal. Now, let us understand how Miller indices are determined. There are three simple steps. In the first step, we find the intercepts of the plane on the three crystallographic axes. These intercepts are expressed in terms of the lattice constants A, B, and C. If a plane cuts the x-axis at a distance A, the y-axis at a distance B, and the z-axis at a distance C, then the intercepts are written as 1, 1, and 1. If the plane is parallel to an axis, it never intersects that axis. Therefore, the intercept is considered to be infinity. In the second step, we take the reciprocals of the intercepts. For example, if the intercepts are 1, 2, and 4, the reciprocals become 1, 1 by 2, and 1 by 4. In the third step, we multiply these reciprocals by an appropriate number so that they become the smallest possible integers having the same ratio. For example, suppose a plane cuts the axes at distances 4, 1, and 2. The reciprocals of these intercepts are 1 by 4, 1, and 1 by 2. Multiplying all of them by 4 gives 1, 4, and 2. Therefore, the Miller indices of the plane are written as open parentheses 1, 4, 2, close parentheses, or simply plane 1, 4, 2. This is the standard procedure used to determine Miller indices. Sometimes a plane intersects an axis on the negative side of the origin. In such cases, the corresponding Miller index is taken as negative. Instead of writing a minus sign before the number, crystallographers place a bar over the index. For example, -100 is written as 1 bar 00. This notation makes it easy to distinguish negative indices. Another important notation is the family of planes. In crystals possessing symmetry, several planes may have identical properties because they are related by symmetry operations. Such equivalent planes are represented using curly brackets. For example, the planes 1, 0, 0, 0, 1, 0, 0, 0, 1, minus 1, 0, 0, 0, minus 1, 0, and 0, 0, minus 1 are all equivalent in a cubic crystal. Together, they are represented by curly bracket 1, 0, 0, curly bracket. This set of equivalent planes is called a family of planes. Now, let us discuss lattice directions. Just as planes have specific orientations, lines inside a crystal also have definite directions. A lattice direction is represented by three integers enclosed within square brackets. These integers are written as u, v, and w. Therefore, A direction is represented as open square bracket UVW close square bracket. A lattice direction is determined by drawing a line from the origin to another lattice point. The coordinates of that point give the direction ratios. The smallest integers having the same ratio are chosen as the direction indices. For example, suppose a line passes through lattice points having coordinates 0, 0, 0, 2, 1, 0, 4, 2, 0, and so on. Although the coordinates are different, their ratio remains constant. The ratio is 2:1:0. Reducing this to the smallest integers gives the direction open square bracket 2, 1, 0 close square bracket. Therefore, this direction is called direction 2, 1, 0. A lattice direction actually represents not just a single line, but an infinite set of parallel lines having the same orientation. If all the signs of the indices are reversed, the resulting direction points in the opposite direction. For example, direction 2, 1, 0 and direction -2, -1, 0 are opposite directions of the same line. One very important property exists in cubic crystals. In cubic crystal systems, the direction represented by square bracket HKL is always perpendicular to the plane represented by parentheses HKL. For example, direction 1, 1, 1 is perpendicular to plane 1, 1, 1. This relationship is generally true only for cubic systems and is extremely useful in crystallography. Now, let us move to the concept of interplanar distance. A crystal contains many parallel planes arranged periodically. The perpendicular distance between two adjacent planes belonging to the same family is called the interplanar spacing. It is usually represented by d sub HKL. This quantity plays a very important role in X-ray diffraction because diffraction patterns depend directly on the spacing between crystal planes. Let us derive the formula for interplanar spacing in an orthorhombic crystal. Consider a plane having Miller indices H, K, and L. According to the definition of Miller indices, the plane cuts the crystallographic axis at distances A0 divided by H, B0 divided by K, and C NOA divided by L. Suppose D is the perpendicular distance from the origin to this plane. The normal drawn from the origin to the plane makes angles phi A, phi B, and phi C with the three crystallographic axes. Using elementary trigonometry, the cosine of these angles can be written as cosine A equals D multiplied by H divided by A0. Cosine phi D equals D multiplied by K divided by B0, and cosine phi C equals D multiplied by L divided by C0. Since the orthorhombic crystal has three mutually perpendicular axes, the sum of the squares of the direction cosines is equal to 1. Therefore, cos square phi A plus cos square phi B plus cos square phi C equals 1. Substituting the previous expressions into this equation gives d square multiplied by h square divided by A0 square plus d square multiplied by k square divided by B0 square plus d square multiplied by L square divided by C0 square equals 1. Taking d square common and rearranging the equation, we obtain the general expression for interplanar spacing. D sub HKL equals 1 divided by the square root of h square divided by A0 square plus k square divided by B0 square plus L square divided by C0 square. This is the general formula for an orthorhombic crystal system. Now let us consider the special case of a cubic crystal. In a cubic crystal, all the lattice constants are equal. That means A0 equals B0 equals C0. Substituting these equal values into the general formula greatly simplifies the expression. The interplanar spacing becomes d sub HKL equals A naught divided by the square root of h squared plus k squared plus L squared. This is the most commonly used formula for cubic crystals. Using this equation, we can easily calculate the spacing between any set of crystal planes if the lattice constant and Miller indices are known. To summarize, Miller indices provide a systematic method to specify crystal planes, while square bracket indices specify lattice directions. Families of equivalent planes are represented using curly brackets, and opposite directions are represented by reversing the signs of the indices. The interplanar spacing d sub HKL gives the distance between adjacent parallel planes and is one of the most important quantities in crystallography and X-ray diffraction studies. A proper understanding of planes, directions, and interplanar spacing forms the foundation for studying diffraction techniques, crystal defects, and the physical properties of engineering materials.